Hi, my name is Wilmer, and today I'll be showing you how to do AP problem number 7. So first off, our first question is, under standard conditions at 25 degrees Celsius, zinc solid reacts with cobalt aqueous to produce cobalt solid. And we first need to write the balance equation for the oxidation half reaction. And since, as you can see, zinc here starts as a solid, so that means it's going to end as an aqueous, so Zn2 plus, so that would be oxidized. So our half reaction would be zinc solid yields zinc 2 plus plus 2 electrons in order to balance out the charge of the 2 plus here. Next, we were asked to write the balanced net ion equation for the overall reaction, and we do this by putting both half reactions like this and just canceling out the terms that cancel out. For example, here the 2 electrons cancel out, so that leaves us with CO2 plus aqueous plus CnS yields Zn2 plus aqueous plus CO solid. Next, we have to calculate the standard potential E for the overall reaction at 25 degrees Celsius, and to do this we need to reference a standard reduction table. And once we do that, as you can see here, the voltage for the zinc reaction is 0.76. It's actually negative 0.76, but since it's oxidized, you flip it, so it's 0.76, and for the cobalt it's negative 2.8, and then you just add these two numbers, so we get negative 2.8 plus 0.76, which gives us 0.48 voltage. So our next problem says at 25 degrees Celsius, H2O2 decomposes according to the following equation, and this is our equation right here, and it also gives us the E standard, which is 0.55 volts. First, we have to determine the value of the standard and free energy change, delta G, for the reaction at 25 degrees Celsius. And we do this by using the equation delta G equals negative NFE. N is the number of electrons canceled out. F is Faraday, which is 96.485, and E is 0.55, which we get from the amount of volts given to us. So once we calculate these numbers, we get negative 106 kilojoules, and we got to round it up to 2 sig figs, so it's negative 110 kilojoules. Now we have to calculate the equilibrium constant K, and we do this by using the equation ln of K equals delta G over negative RT. Delta G is our standard free energy, which is negative 110 kilojoules. R is 0.00831, and T is negative 298. So once we plug in the numbers and calculate this, we should get that K equals 1.96 times 10 to the power of 19. Our following problem says the standard reduction potential E for the half reaction O2 plus 4H plus 4 electrons equals 2H2O8 2H2O has a value of 1.23 volts. Using the information in addition to the information given above, determine the value of the standard reduction potential E for the half reaction below. So we have to determine the potential E of this reaction, and we do this by basically balancing out the overall reaction using both reactions. As you can see, we've crossed out the H2O liquid here, and we've multiplied both reactions by 0.5 in order to get O2 plus 2H2 plus 2 electrons yields H2O2, which is our equation here that we are supposed to get. And once we do that, we add these two numbers up, and we should get that E cell is 0.68 volts. Our last problem says in an electrolytic cell, Cu is produced by the electrolysis of CuSO4. Calculate the maximum mass of Cu that can be deposited by a direct current of 100 amps passed through 5 liters of 2.0 molarity CuSO4 for a period of 1 hour. And we do this by doing a stoichiometry. So here are 100 amps, and we'll multiply that by 3,600 seconds and divide that by 96,485, and we multiply by 1, divided by 2, then we multiply the molar mass of Cu, and we would get that the maximum mass of Cu that can be deposited by a direct current of 100 amps is 180 grams. Thank you for watching. That's it for today.